Hi, this is Fred Evers. This is my final presentation, long version for CSCIE 89 Deep Learning at Harvard Extension School. Um, from the start, I'm going to let you know that I'm going to kind of wing this because I am exhausted. This is one of the hardest things I think I have ever done in my life. That said, here we go. The topic of deep learning is a very complicated one. I was surprised and somewhat disappointed to learn how hard it actually was. But the topic involves a couple of important issues. You know, uh, Summarizing text is an absolutely essential technology. There's so much text around the world that we need to be able to get through it as quickly as possible. The technology that we will discuss here on this video promises to make that a little bit easier, which is a very good thing. As it turns out, there are two fundamental approaches to text summarization. The first one is called extractive summarization, and that's a more typical approach. It involves a kind of cut and paste approach to a source document where people will go into a source document and essentially edit it. This has been automated to some extent. But what is more interesting to us in this class is called abstractive summarization, which uses an unsupervised learning technique of short-term neural networks to be able to extract information independently of any human interaction. And in the course of this presentation, I will discuss one very simple kind of hello world related step through of a project from TensorFlow to fulfill the requirements that I did something with code. But the more important work that is in this presentation relates to the analysis of a recent expansion of the released Google Brain project on text summarization by a woman named Abigail C. And we will get to that shortly. So here we go. Um, okay, so in 2016, Google researchers released an open source version of an experimental abstract summarization tool. Since then, several new implementations have been released and are available on GitHub. So I will discuss one recent implementation of that in some level of detail. I'll also talk about points of commonality between the basic version that was released by Google, which is called TextSum, and the new version, which is of great interest to me, called Pointer Generator. And then finally, I will make reference in passing to some information that I have gleaned from web searches and so on, where it appears that Salesforce.com has come out with an even better text version summarization. However, their code is not available, so I have nothing but the paper they published to base my opinion on. The paper they published does have some measurements which indicate that their version is significantly better, but I have no idea exactly why. I do not have access to the code. So there will be very little attention given to that. Typical architectures for text summarization include LSTM, long short-term memory, or GRU, graded recurrent unit networks. They typically also use an encoder-decoder architecture, which is a symmetrical organization of neural networks with an embedding layer which contains the fundamental representation of a vocabulary model which contains a large corpus of text from which the model can draw for purposes of generation. Finally, there is typically a projection layer after all of the network layers where the content is projected into one single dense layer, which allows for calculation of loss. Some of the problems that are frequently seen with text summarization in the abstract method that I've described are inaccuracy. Often you see gibberish being generated by such models. Neural networks ultimately are forgetful, and so it's very difficult to program memory into them so that they can look backwards at the prior state of their networks in order to develop a greater sense of context. And we all know that context is what determines meaning in language. Finally, they tend to be extremely repetitive because they draw upon the same collection of vocabulary, and they tend to reproduce or select the same representation or the same word to fill in a particular gap in the time sequence. They select the same word repeatedly, which presents a problem because it's very, very boring. The text sum version, which qualifies as a kind of a baseline version for what we are about to study, adds a few additional features to the standard model I just described. One of them is a layer which represents attention, which preserves sentence context to address the idea of forgetfulness that I mentioned just a few seconds ago. So here's a representation, a diagram taken from our class, which shows the attention layer in between the encoder and decoder sides of the model. It also shows the embeddings for the source layer, and in a translation model, what you typically have is a pairing between a target embedding, which would qualify as a collection of strings, which are the strings that the source language maps to, right? So that a model is trained by comparing a collection, a large collection of source strings against target strings in the target language to represent the most common translations of the source string in the target language. A neural network that is devoted to text summary operates in a similar fashion. In addition to that, what's significant in text sum code available via open source on GitHub, for which there is a link, you will see that there is a attention mechanism, which is now called wrappers, which is now built into the TensorFlow contrib sec to sec module, so that this material, which has been under development, will now be available by downloading. And I think this is from TensorFlow 6 and forward. This is an example of the architecture that is typical of the Google Text Sum. You see, of course, there's an encoding layer represented on the left, source text. On the right, you have the decoder. And this also shows the time sequence rendered as if showing it unfolding. On the left, we see a string that is entered. And on the right, we see a partially decoded string related to an example where the topic is an attempt to create a summary of a model example, which is an article which describes a soccer game as being reported. It says here, Germany emerges victorious 2-0 against Argentina. We all know Argentinians are the best soccer players. The Germans beat them. If you look up above in the green, we see that from the vocabulary, this model has extracted a word best to replace emerge victorious in the source text. What I'm most interested by is a model that I discovered on the internet through GitHub, which is by a woman named Abigail C., who is a PhD student at Stanford University, who has generated a new model which she calls a pointer generator. This model is available in both Python 2 and Python 3. And I would like to talk a little bit about some of the features that differentiated from the previous diagram that I just showed you. Mention here is also made of the Salesforce model that I spoke of a moment ago, and I have no code to show you, but ultimately I will show you the scores that Salesforce has advertised as demonstrating that their newest version is better than Abigail C's pointer generator. But I only have code for pointer generator, and that's what I will discuss. So if you look at the very top of this slide, you see that pointer generator adds one additional layer to the previous slide. We saw a context vector, which acts as a form of memory and helps to keep the neural network conscious of what has preceded it, what networks or what words it has already translated, also the context in which those translations take place. And so that over there on the right in the green, you see that there is a vocabulary distribution, which represents the collection of hard-coded, embedded vocabulary that the model has to draw on. At the same time, this particular model allows for a selection to be made between terms that are out of vocabulary, which are derived from the source text itself. So if you look at the very top, you see that there's a formula where there is a probability distribution analyzed and weighed. On one side, on the left, you see the probability of using the source code, a string, whereas on the right, you see the decision being weighed to extract from the vocabulary itself term and insert it into the final distribution for selection into the prediction for the translation or the summarization. These are some of the features that are available in the pointer generator model. Attention distribution, which we saw in the previous slide. There's a context vector, which assists in the memory. There's an additional feature called coverage, which is a normalized distribution over the force document words that represents the degree of coverage that those words have received from the attention mechanism thus far. These features produce a vocabulary distribution, which is a probability distribution over all words in the vocabulary, including the strings from the source text itself. And the final distribution is a subset based on a logarithm of the probability of both the coded vocabulary collection and any new strings which have been added to that final distribution from the source text itself. So this highlights the idea at the very top that I just described, where that decision is taken. The probabilities on both sides are highlighted by the circle, and it is a decision made by the system whether to use a word from the source text versus the vocabulary, the embedded vocabulary, and that's what is unique about this particular system. Here is some of the code from the representation in the version of this code available on GitHub. This highlights the idea that where out of vocabulary strings are appended to the strings made. There's a final distribution from which the predicted words are chosen. You can see here, this is the code which makes that selection, where we see that the hypotheses are sorted by average log probability, and the highest probability is selected and inserted as the term for the summary. Finally, this type of application depends upon a previously undiscussed measurement standard. It is called ROUGE, and ROUGE stands for Recall-Oriented Understudy for Gisting Evaluation. ROUGE is a set of metrics for evaluating automatic summarization of texts as well as machine translation. We have studied machine translation in this class, but we have not spent much time on summarization. but they are very closely related fields.